So we're gonna graph this like I'm teaching my Algebra 2 kids how to do exponentials right now. And when we graph them, we make a little table. We're gonna make a table. Okay, we're learning how to graph something, we're gonna use a table to graph it. So our theta is our independent, our radius depends on theta. We're definitely gonna start at 0. And let's go by pi over 6's. So we're gonna go pi over 6, pi over 3, pi over 2. 2 pi over 3, 5 pi over 6, pi, 7 pi over 6. We're not going to do this a bunch, don't worry. 5 pi over 3, we stop.
Not 7 pi over 6.
6, yeah, sorry. And so now we're just going to plug those in and work this out. The nice thing is this is just 2 times the angle. So some of these are going to be kind of quick. For example, the first one. What's 2 times the angle on the first one? 0. Okay, good. All right. So what I would do is just get your calculator, go pi over 6 times 2. Whoops. Helps if you turn it on. You're just doing this in the main part, so no, it doesn't matter. 1.05 about for the first one. Is that what you guys got?
Yeah.
Oops. So that should go pretty quick, making this table. And then we're going to sketch it. So on your homework, here's what I expect a sketch to look like, okay? And part of this is paying attention. We need to get out to a little bit more than 10. So I would probably draw these in. I'd probably make my circles count for 2 because I don't want to have to draw out 11 circles. I'd rather draw out 5 or 6. So pay attention to what your values go to determine what you're going to count your circles with. So 5. 1, 2, 3, 4. That's good enough. And then because we counted by pi over 6's, maybe draw those in. Notice I didn't go past 5 pi over 3. That's where we stopped. I did 5. When they're not even, they look kind of fun. It's okay. It's a sketch. Yes? Did I? Oh, Miss White failed. I did. So what would the next one of these be? Oh, I can't believe I did that. Caitlin, thank you. Oops, I got a 6. I need a 6. No, that's right. We're not done. Oh, you know why I stopped there? I was copying in the book. Where'd you get these ones? What's 4 pi over 3 times 2? Not 5. Oh, thank you. I would have been really mad at myself. Okay. Sorry about that. Totally screwed that up. Shouldn't have just copied the book. Should have actually done it. Okay. So now can we just plot the points?
Yes.
So at 0, it's at 0. So you start at the pole. And then the pi over 6, we go out 1.5. So barely at all right there. And then a pi over 3, we're 2.9. Pi over 2 at 3.14. So what's happening to our numbers? We're going out. It's not at a constant rate. And then you connect them in the order you graph them. So what shape is that? It's a spiral. These almost all of these have special names actually. This is the Archimedes spiral. So anything that looks like r equals some number times theta is going to give you an Archimedes spiral. So that's one of them. Let's do another one. We'll do another point by point, and then I'll teach you rapid sketch. It's kind of cool. You're just plotting these points. Okay. So here we go. Let's do pi's over 6's again. And we may not have to go out as far, so I'm just going to do a few, and then we'll see if we need to keep going. We'll stop right there and see what happens. Because what happens with a lot of these is after a while you'll start repeating values, and then you don't need to keep plotting over the same point again. So we're going to see until we repeat. Okay. And they told me theta is in radians in the directions. So make sure you're in radian mode. And I am. And really all I'm going to do is write 4 cosine of 0. Well, what's the cosine of 0? 1. 4 times 1 is 4. Oh my god. Okay. So in this one, I'm going to write 4. In my calculator, I'm typing 4 cosine pi over 6. Oopsies. Have we repeated yet? Nope, so let's keep going. Haven't quite repeated yet, so let's go a little bit more. What? There's a pi button.
No, but instead of having to do second every time.
Oh, that's what you mean. You mean have it made the k function.
Yeah,
Okay, so let's try these two and see what happens. Oh, what's happening? What happened right there? It repeated itself. So we actually could stop right there. As soon as you start repeating yourself, it's going to start circling back on itself. So, and we don't have to draw that many circles. Let me probably stop. Okay. Just started going, couldn't stop. Okay. So let's plot. So at angle 0, how far out are we? Blah, blah, blah. So you're gonna go 1, 2, 3, 4. Then at pi over 6, we're at like 3.5. And then here we're at 2. And what happens at pi over 2? We're at 0. And then at 2 pi over 3, it's a -2. So instead of going towards it, I need to go backwards, yes? And then it's 5 pi over 6, it's -3.5. If I'm not mistaken. And then at pi, it's -4. And at 7 pi over 6, it's -3.5. So see how the points kind of keep repeating themselves there?
Yeah.
So really, this shape right here is actually a circle. Actually, there's a whole chart that will tell us all these. So that's a circle. Different, and we're gonna find out. We're gonna explore some of these. When you change this number or even the number in front of theta, it changes the graphs to look differently. So it's hard to kind of generalize right now. Are we okay with point by point? Yeah. Okay. The next one, I actually like it better. It's called rapid sketch plotting. It relies upon knowledge of the quadrantals. Okay. So, this is rapid sketch. So we're going to use quadrantals. So the chart looks a little bit scary and overwhelming, but once you get the hang of it, it actually goes really, really fast. Okay. So for the rapid sketch, our independent variable is still theta. And so we're going to look from 0, as 0 goes from 0 to the next quadrantal, which is pi over 2. And then from pi over 2 to pi. And pi to 3 pi over 2. And then 3 pi over 2 to 2 pi. We always want theta, or whatever the cosine of whatever, the sine of whatever. If that was a 5 theta, I would want the 5 theta to be my quadrantals. Okay? So whatever you're taking the trig function of, you want that to be the quadrantals. Here's why. So we have our thetas, and what we're going to look at, we're just going to branch out just a little bit. So now we're going to, okay, well, what's cosine of theta? So this is where it's really handy to have this drawn out. So, because now I'm looking at the cosine of theta. Well, what's the cosine at 0? 1. So it's going to go from 1 to, where's the cosine of pi over 2? So from here to here, it's going to move from being at 1 back to 0. And then at pi over 2, we start at 0, and we go to -1. And then at pi, we're at -1, and we go to 0. And then we go from 0 back to 1. And now we're going to branch out just a little bit farther. So now we're going to look at 5 cosine of theta. Well, I already know what the cosine of theta is. What am I going to do to all those values? Multiply them by 5. So this goes from 5 to 0, 0 to -5, -5 back to 0, and then 0 to 5. And then the last one is now we're going to put the whole thing down, which is 5 plus that. So what are we going to do to all those numbers? Add 5. And so this column, the first column and the last column, that's what we're going to graph.
You start with theta on all of them and go to the left.
So I'm gonna move this up. Bless you. Yeah, I still see that. Okay. And I need to get out to 10, so I'm gonna count by 2. My circles are gonna go by 2s again, if that's all right. Saves us some time. Okay. So at 0, where do we start?
10.
0, we start at 10. And then at pi over 2, where do we go to? So kind of, you're going to loop it because they look loopy. Maybe I should have done that later. I don't know. Okay. Are you okay with the first one? It's all about movements.
We connect them.
Yep. They're going to loop. At 0, you start at 10. And then at pi over 2, you go to 5. And then you just connect them. And we probably could connect them later. But I already did it. And it's in pen. So I'm committed. Okay.
And each your circles is 2, right? Yours, like on your drawing.
I graphed this one and this one.
Like nobody's circle.
Oh, yeah, 2. Yeah.
Okay,
So then at pi over 2, we start at 5. We're already there. And then we go to 0. So we curl back to 0. And then we start at 0. And at 3 pi over 2, we go back out to 5. Now, it's really tempting. And just because I looked ahead, it curls back this way. You'll get better at these. I would also graph these to make sure you're graphing them right when you do this. And then 5 pi over, or back at 2 pi, we're back out at 10. Yep, these are actually called cardioids.
Can you graph all the different kinds like that? Or just this kind?
No, all the different kinds you can graph like this. There are some that are harder to graph like that. Like circles, the circle would have been really hard to graph like that because they would have just said go to here, to here, to here, to here, to here, to here, to here.
Yeah.
Which, and like the more you do, the better you get at looking at them. That's a cardioid. No, I'm just telling you what they're called. They might ask you what's the shape, but I'll give you the page where they tell you all the shapes and they give you all the general formulas. But they're kind of fun. They have different shapes we're not used to seeing, so it's kind of cool. We're gonna do another one, rapid sketch style, okay? So, Remember how I said whatever you're taking the trig function of, you want that one to be the quadrantals? What are we taking the trig function of? 2 theta. I need to graph theta, but right now I know I want my 2 thetas to be my quadrantals. So whatever the angle is in here, you're going to make the quadrantals listed there. So 0 to pi over 2. Pi over 2 to pi. Pi. 3 pi over 2. Sometimes we have to go farther, but we don't know until we get started, so... Actually, I'm going to save us some heartache and tell us what we do. Because the angle is doubled, when we go backwards to theta, what are we going to have to do to go from 2 theta back to theta? We have to cut everything in half, right? So what's going to happen is this really is just going to be one period movement through for theta. So I had to double it because that was doubled there. So we went twice as far in this column. Is that okay? I'm not going to plot with this. When you plot a point, it's the radius and then theta. Is this theta? That's 2 theta. I need to figure out what just theta is. So if I want my 2 theta to be my quadrantals, though, because the sine of a quadrantal, I can get it super quick. Right? But in order to plot it, I need to know what just theta is. So how do I go from 2 theta to theta? We're going to divide everything by 2. So this goes 0 to pi over 4. And then pi over 4 to pi over 2. It's making everything, we're counting by quarters. We're going to plot in quarters instead of by the halves. And then this is going to be 3 pi over 4. 3 pi over 4 to pi. And then 5 pi over 4 to 3 pi over 2. So our thetas actually end up doing one full rotation through. But we want what we're taking the trig function of to be our quadrantals. So now let's do our quadrantals. Now we're looking at the sine of 2 theta. So what's the sine at 0? 0. And at pi over 2? 1. And then it's going to go 1 to... At pi, it's at 0. And then 0 to... -1. -1 to 0. It's a pattern. After a while, you don't even have to think about it. You just go. And what's the last step for this rapid sketch, or this chart? You'll multiply them all by 6. And we use the first and last column to plot. Are you guys okay with the chart? Okay, so I'm going to have to move this to graph it, okay? So you have it in front of you. Okay. We need to go out by 6. So I'm going to count by 2s, but I'm going to make my circles a little bit wider. I guess I could fill them in between if I wanted, but I'm okay. I'm okay. You're okay. And my thetas are in pi's over 4, so I'm going to draw my pi's over 4 in. And then we start. So, where does it start at? 0. So it started at 0, and then at pi over 4 we go to 6. And so 6 is out here. It's everything in this world it's loopy. Okay, so make it loopy. And then we go from 6 back to 0. So that's the first 2. So then, now the next one was the, so we start at 0, and then at 3 pi over 4, we're going to go negative 6. So do I go this way, or do I go back? You go back. So we go to here, and then the next one, it goes back to 0. Is that okay? So now we're here. And then at 5 pi over 4, we go out to 6. And then we go back. Is that okay? And then the last one, it's at 7 pi over 4, but it's a negative 6, so we go back out. So what does it make? Looks like a flower. They call this a 4-leaf rose. There's also a 3-leaf rose. And if your circles were symmetrical, it would look a lot cooler. Okay. Once again, this is the beauty of graphing this way. Okay. We got one more example, and then I just have stuff to show you in the book, okay? So the last example, we're going to finally do this in our calculator. We get to use a new mode. So, in your calculator, hit mode. Make sure we're in radians, but we've lived in function mode, we've looked at parametric mode, and today we're going to look at POL, which is polar. Also, if you look down at your variable button, I'm kind of pointing to it. I don't know if you can see me point to it down here. When you're in function mode, you have an X. When you're in parametric mode, you have a T. When you're in polar mode, you have a theta. So when you hit this button, instead of an X, you're going to get theta. So that's what that button is. It depends on which mode you're on and which variable you're going to get there. Sequential, I haven't used that one. Not that I recall. Maybe I have someday and I don't remember, but. So let's go to hit y equals. And now instead of y equals, there are equals. Okay. So let's look at the first one we graphed today, which was 2 theta. And this is from the very first example, yes? And before you hit graph, I'd like us to go to our window. Because our window is now changed. We have a theta min and a theta max. And if you look at the first example, they told us we wanted to graph from 0. And then they wanted us to stop at 5 pi over 3. So in the theta max, I'm going to hit 5 pi over 3. And then I'm going to hit enter. I'm not there yet. Are you okay with the theta steps? Or the theta? Now, the theta step, that means how often do you want me to calculate a point? If you make this number really big, is it going to calculate a lot of points or not many points? Not many. And so your graph is going to look crazy insane now. If your theta step is too big, You're going to be like, I don't know what this is. And I'm like, I don't know either. Your calculator is broken. And I'm like, oh, your theta step. Ha, ha, ha. So, theta step, leave it small. I don't even change that number. I don't even know where it came from. I just know it's there. I don't change it. Okay. This we can probably go from negative 10 to 10. And then for the y min and the y max, negative 10 to 10. I've obviously been doing something else in my calculator. So the x and y's just make them negative 10 and 10. We can adjust this as needed. Now we're ready to graph. You ready to see it?
Wait. Did you miss it? Well, okay, so it says like XSCL.
The x scale. Do I ever change the x scale?
Yeah, yours said 1 and mine is like...
I don't care what the scale is. I could care less. I've never once changed it. You guys have asked me that all the time. Never. I never change it. I don't use the scale to tell me anything. I can care less. Isn't that cool? Yeah. Go back to your window and change the theta max. Change it to 3 pi. See what happens. Change your theta max to 3 pi. It kept going. Yeah. When you change that to a bigger number, it keeps calculating more points. We told it earlier to stop at 5 pi over 3 because that's what they told us to do in example 1. But let's do the circle. So let's go back to your y equals. And the next example we did for cosine theta. So let's see what that looks like. Now this doesn't look much like a circle. Here's how you can make it look better. If you go zoom and then hit square, hit zoom in number 5. It squares the window up so things aren't distorted. Because our viewing window it's not symmetric. And when you do standard, it makes it kind of rectangular and long, so it stretches things out. So the zoom square makes everything proportional, so it doesn't have that distortion. So it actually looks like a circle. Kind of cool? Okay. Let's do this one. The 5 plus 5. Cosine theta. That was the cardioid. Isn't that cool? No, you mess with them. And then the last one that we looked at was the flower. So 6 sine 2 theta. The 4-leafed rose. Aren't those cool? Okay, I lied when I said these are all curvy. There's a few that aren't curvy, but those aren't the fun ones. If you look on page 447, we don't look at these three very often. We looked at that one in an example, in the homework yesterday, then 72, when it said theta equals pi over 4. We got the line y equals x, right? That's where it is. So you can make a circle where it's on the origin. You can make a circle that's over here. It's up there. You make cardioids go in different directions. Oh, I'm going to flip. I'm not there yet. Slow her down. Slow your roll. Here's the 3-leaved rose. If you notice, what's the difference between the 3-leaf and the 4-leaf?
They're moved around.
Look at the equation. 3 to 2. Actually, let's do a little experiment, shall we? Let's go back to our calculator. So, leave the 2 theta in there. So now, what if we go 6 sine of, let's try 4 theta. I don't remember what this does. I just wanted to see.
Whoa, you're messing with mine.
So if I turn the first one off,
Whoa. Wow, it's a beautiful flower.
I turn the first one off. What happened to our number of petals? They doubled. So what if you change that to 6 from the original? Would it triple? Oh my god, super cool. So the even numbers are going to give it even number of petals. What do you think the odd numbers are going to give us? Odd number of petals. Isn't that cool? I think they're pretty cool.
What happens if you put an odd number?
Try it.
Well, I'm already at 8. Look.
I know, it's crazy.
Go 10.
So this, I can never say it right, so I'm not going to even try. But if you get a function that looks like this is what it looks like. Yeah, I can't say it. And then we also looked at the spiral today.
Oh, never gonna stop. How disappointing.
Shh, quiet please. We're not, there's no more examples, this is just talking. So, if you look here, I don't think I've ever read this before. This is actually by the U.S. Coast and Geodetic, I can't never say it, survey, for oceanography. It's, the direction and magnitude of tides in the San Francisco Light Station. They make kind of a polar looking graph. Kind of cool. So, oh my. Oh, you can't do that one on your calculator? No, you can't. $4.50. I only want you to do one of the point by points. So I want you to question 1. No. Then 7 through 14 are on your calculator.
Oh, that's right.
No, this is on your calculator. You don't even have to write anything down.
You know? Why are we doing that?
I want you to play on your calculator.
Come on, man.
I'll let you do 17 and 23.
I don't want to pass my books.
29. 31. Most of these are calculator that I'm giving you right now. And 39.
Wait, what was that last one?
39. I'm fine with that. Oh, whoops. This is just supposed to, like I said, this section is just kind of exposing you to another way of graphing.